Check it out now, y'all.
nanoHUB-U, online instruction.
So welcome to module 5.3. Now, as you may recall, in the first module, I tried to explain why there is this asymmetry between absorption and emission that needs to be obeyed in order to comply with the second law. And the two tried to show that relationship. And in the last module, I tried to explain how one can understand this asymmetry between absorption and emission as being the result of this entropy-driven process, where you're basically trying to go to states where there are many, many configurations available. And for absorption, there is fewer states available. For emission, there's more states available. Now, this idea leads naturally to this law of equilibrium, this general law of equilibrium, which says that if you have a system, with lots of states, say each state corresponding to some energy E and some number of electrons. In fact, for this discussion, let's leave the N out of the story. We just talk about different energies being available, and we'll use this particular relation. And with the idea that, if electrons are being exchanged, then we, instead of E, we'll use E minus mu N. That idea, we'll back to this. Now, so if you have different energies available, then the basic law of equilibrium is that the probability the system will be in a state with energy E is proportional to e to the power minus EI over KT. It's proportional to that, and this proportionality constant is usually written as this Z. And how do you find Z? Well, the idea is all the probabilities summed over all states must add up to 1. And that then allows you to figure out what the Z should be. And what I'll show a little later in this module is that these general equilibrium laws that I've stated, the Fermi function for electrons, or I think in week 5 of part 1, we talked about the Bose function for phonons, same for photons. We'll see that those are all special cases of this same law. Those functions don't quite look like what I've written here, but what I'll try to show is that it really follows from here. But this is the general law of equilibrium that applies to all systems in equilibrium. And this you can understand as simply the result of this asymmetry between absorption and emission. That is, supposing we consider two states, let's say having two energies, E1 and E2. Now, if the system happens to be in 1, I could call that, say, the probability it is there is 1, and it wants to go up by absorbing a certain amount of energy. Let me draw that with a red. So, in order to go from E1 to E2, it would have to absorb an amount of energy E equal to E2 minus E1. So let's say it absorbs a certain amount of energy E. That's what we have called P of E. And at equilibrium, that must be equal to the rate at which, if the system is here, it comes down by emitting an amount of energy E. So this must be equal to P2 times the probability that it will emit. And what that tells you then is that P1 divided by P2 must be, or let me write it the other way, P2 divided by P1 is equal to P of E divided by P of minus E. And this is the thing that I said earlier. The basic rule is that absorption and emission must have this ratio of exponential minus E over KT. So what that tells you then is that P2 over P1 must be equal to, as you notice, E is actually E2 minus E1. So you could write it as exponential minus E2 minus E1 over KT. So the equilibrium probabilities of finding the system in different states 1, 2, etc. must be such that their ratio obeys this relation, because then it will ensure that the rate at which things go up would be balanced by the rate at which things go down. And you can see that this is automatically satisfied if this basic law of equilibrium holds. Because, you see, what I've got here, you could write as e to the power minus E2 over KT divided by e to the power minus E1 over KT. See? And of course, in this ratio, I could easily divide this by Z and divide that by Z. And the basic law of equilibrium tells me this is P2, that's P1. So it works perfectly, you see? So one could say that this general law of equilibrium kind of is a consequence of this asymmetry between absorption and emission. Okay. Now, the next point I want to make is how from this law we can obtain the Fermi function. So consider an electron. So I guess I'll write it here then. So supposing we have an electron occupying which has one state available. This is epsilon, some state. Now, the part that needs some getting used to is that this is what you call a one electron picture. That's what you call a one electron level. And in order to apply a relationship like this, we need to think of this many electron picture, or what's sometimes called Fock space. FO. So we need to adopt this, think in terms of this Fock space picture, or this multi-electron picture. So the way you think about it is, I've got one level. It can either be full or it can be empty. You could have an electron there or not have an electron there. Okay? So that then corresponds to two states. One state has zero energy. Another state has an energy epsilon. And this state has one electron in it, zero electrons in it, so that's N, this is E, and this has one electron in it. So in the multi-electron picture, you could have zero electrons or one electron. Now you cannot have any more because electrons obey this exclusion principle. Okay? Now, when I want to apply the general principle, and the general principle in this case, of course, number of electrons is also involved. So earlier I had said that I was writing E, but then if electrons are involved, you should use E minus mu N. So let me put that N. So it is EI minus mu Ni over KT. So what that tells me then is that the probability the system will be here is proportional to e to the power minus epsilon minus mu over KT. Why? Because energy is epsilon, number of electrons is 1, that's it. And the probability the system will be here in the zero state is e to the power 0, which is 1. So what we have then is P0 is equal to 1 over Z. That's the probability of having 0 electrons. And P1 is equal to e to the power minus x over Z, where x is equal to, x is defined as epsilon minus mu over KT. So how do I find Z? Well, the answer is you have to just add those two, equate it to 1. So what that tells me is when I add those two, 1 plus e to the power minus x divided by z, that should be equal to 1. So z is equal to 1 plus e to the power minus x. Okay. So now I am ready to find P0 and P1. I could write, let me write it here. So I could write P0 as 1 divided by 1 plus e to the power minus x, that's 1 over z, and P1 is e to the power minus x divided by 1 plus e to the power minus x, which you can write as 1 divided by exponential of x plus 1. And you'll notice, of course, that's exactly the Fermi function. It tells you that when you have a level epsilon, what is the average number of electrons in there? Well, the probability of having 0 electrons is that one, probability of having 1 electron is this one, and it's given by the Fermi function. And if you looked at P0, you'd find it would be basically 1 minus this quantity. Okay. So what this shows is that the general law of equilibrium that I wrote down, that we discussed, gives you the Fermi function. Okay. Now let me quickly show how you can get the Bose function from it, starting from that same relationship. So there the idea would be that you have a photon whose energy is this h bar omega, and in that state you could have 0 photons, or you could have 1 photon, or you could have 2 photons, or you could actually have any number of photons up to infinity. That's where it's different from the electron case, where electron was 0 and epsilon. It was just 2 states. Here it is many, many states, infinite number of them. And what you want to know is the average number of photons. That's this Bose function. So the way you'd write this down then is, you'd say, well, the probability of having n photons is proportional to e to the power minus n h bar omega over kt, and divided by z. Okay. So how would you find z? Well, you could say, well, summation Pn from n equals 0 to infinity would look like, and if you add them all up, it would be like sum of e to the power minus nx from 0 to infinity divided by z. And that should be equal to 1. So that tells me that z should be equal to this summation. And that summation is easy to do because it's a geometric series. You see, it's like 1 plus e to the power minus x plus e to the power minus 2x, etc. And as you know, that series is easily added up to give you this one. I'll write it here. So this is really z. Z is the summation over e to the power minus nx. That's what is z. And that is then 1 divided by 1 minus e to the power minus x. Now, if you want the average number of photons, which is what the Bose function gives you, see, then the way you can write it is, the average number of photons is sum n npn. See, that is, Pn is the probability of having n number, and so n times Pn, if you add it all up, that gives you the average number. And that comes to, as you can see, you'll have summation over n, and Pn is e to the power minus nx over c. So, looks like we need to do another summation, but this is where you can use a little trick. So, let me write this result up here. Summation of this average n is equal to summation n e to the power minus nx from n equals 0 to infinity, and then divided by z. And what we found already is that z is equal to this quantity. Now, what you can do, you see, is supposing I take the derivative of this with respect to x. So when you take the derivative with respect to x, what you get is summation n e to the power minus nx with a minus sign. So the derivative of that, you see, pulls down the n. And that should be equal to derivative of this quantity, which is 1 divided by 1 minus e to the power minus x whole square. I'm taking the derivative, and then I have to put a e to the power minus x on top. And there's a negative sign here. So that negatives cancel. So you see this summation of n e to the power minus nx is given by just the derivative of that, essentially, with the minus sign taken off. So now it's quite easy to evaluate what we were trying to do, this case, where you see we have the expression for this part, which is the numerator, which is e to the power minus x divided by 1 minus e to the power minus x squared, and divided by z. Z is 1 over 1 minus e to the power minus x, so that's like multiplying with 1 minus e to the power minus x. And this cancels that, and so what you get then is 1 divided by e to the power x minus 1. And that's the Bose function, you see. E to the power, you know, I had written x for h bar omega over kt, so that's it. Minus 1. That's it. So the point I'm trying to make here then is that we had this general law of equilibrium, which says that any system, if it has a bunch of states available, then it will occupy these different states according to a probability given by e to the power minus ei over kt divided by z. And this applies to any system. And when you apply it to just a system with one electron, with an electron having this one level available, you get Fermi function, tells you the average occupation. When you apply it to this photons or phonons with one state available, h bar omega, in which you can have many, many of them, you get the Bose function. So all this kind of follow from there, and of course, and this is a general principle that you could apply even when you have interacting systems.